Welcome back, E&M students. This is our third video lecture about properties of vectors. And it's going to be a little different than the first two, where we were, for the most part, reviewing the techniques of what is called vector algebra, doing algebra with vector quantities. This video is going to introduce probably something quite brand new for many of you. And we're going to talk about how a vector quantity is changed or transformed when you rotate the axes of your coordinate system. So let me start with just some kind of preliminary comments. And the first comment I want to make is that for years now, we've been teaching you that a vector quantity is a quantity with a magnitude and a direction. And for all the physical applications we've come across, that's worked okay. But now I want to emphasize that that's really not good enough. If I think of a vector as a quantity with magnitude and direction, that will end up eventually leading me astray. And I'll give you an example from real physical application. If you study solid-state physics, one of the things you might study are the properties of metals, electrical conductors. And what makes a metal an electrical conductor is the presence of a very large number of electrons in the body of the conductor that are free to move around. And of course, the conductors are three-dimensional, so there are three distinct perpendicular directions that the electrons can move in. Now, the crystal actually consists of a bunch of atoms in a lattice configuration, and depending upon how those atoms are actually spaced, you can have the situation where, as an electron moves in one direction versus another or another, its interactions with the lattice are different. And it's the interactions of the electron with the lattice that give rise to what we call its effective mass. You can actually measure this. It's like a measure of their inertia. And it's not necessarily the regular mass of an electron that you learn about in introphysics. It's the effective mass. That's the result of how the electron is interacting with the lattice. And for many crystalline lattices, the interactions of the free electrons in one direction may be different than in the other directions. And so the effective mass of the free electrons can be different depending upon the direction the electron is moving in. And so effective mass appears to have a directional aspect, different value of it depending upon what direction you're going in. Now, under our discussion of a vector as something with magnitude and direction, we would be inclined to think, so, effective mass is a vector. But it is not a vector. Turns out effective mass is what's called a second-rank tensor. So this is just meant to be an example of how the simple thought of vector as a quantity with magnitude and direction can eventually lead you into confusion. Okay? All right, so we need to have a better understanding of what it is that makes a vector a vector. In other words, what's the definition of a vector quantity if it's not something with a magnitude and a direction? All right, so to develop that new definition of a vector quantity, let's take something we know full well is a vector quantity in physics. And that we will take to be the displacement of a particle that has been moving around. Okay, so let's focus on the displacement of a particle, and let's just limit ourselves right now to two spatial dimensions. We'll bring up the third dimension soon enough. Okay? And so let me draw an XY coordinate system, and I will label the axes. And of course, the axes go to left and downward, but we'll just stick to drawing the positive directions. And let's say we had a particle moving around, and it started out at point A, might as well put that at the origin, And it moved around by whatever path, I don't care what path it took, but it ended up at a point B there. We know how to represent its displacement, and displacement from the origin is often just denoted as r vector. So I'm going to draw an arrow in a straight line from A to B and label it r, and I'll put the arrow on it because we know displacement is a vector quantity. Okay? All right. And let's go ahead and sketch the components of that vector in this coordinate system. Not too hard to do that. I go along the x-axis until I am directly underneath point B, and that's the x component of the displacement vector, which I'll just label with an x. And then make a 90-degree turn and go straight up until I get to point B, and I will label that the y component. And it's also convenient to label the angle of the position or displacement vector with the plus x-axis. We'll call that theta. Then we're all familiar with how to write down the components of that displacement vector. We'll call them x and y. But note, some books will call them r sub x and r sub y because they are the x and y components of that vector labeled r. And just from trig, that will be, for the x component, take the entire magnitude, r magnitude, take careful notice of my notation, times the cosine of theta. Good old trig. Whereas the y component of that displacement would be r magnitude, the hypotenuse of that right triangle that you see, times the sine of theta. Very familiar with that. Okay? All right, so that's our quintessential example in physics of a vector quantity. But now what I want to do is I want to see how the components of that displacement vector change if I do one particular operation with the coordinate axes. I want to rotate them. About the origin, I'll rotate them counterclockwise by some angle phi. Okay? So now what I want to talk about B is a rotation of the axes. That's an example of what we call a transformation in physics. So here's the question we're asking. What happens to the components of the displacement vector for our particle, r arrow, if the axes are rotated by an amount phi, keeping the actual r arrow fixed. That's important. I'm not going to rotate the r arrow. That's important. I'm only going to rotate the axes. Understand what I'm saying? So let me draw a new picture. I'll draw it right down here. So I have the original axes. X and Y. Okay, fine. And now here come the rotated axes, rotated about the origin, point A, counterclockwise by an amount phi. So the x will become a new axis so that we will call it x bar. We don't want to confuse it with the old x-axis. Okay? Where this angle right here is phi. And then the y-axis, the new y-axis, which we'll call y bar, has to be perpendicular to the x bar axis. So y bar is rotated from y, also by the amount phi. So x and y are perpendicular to each other, and x bar and y bar are perpendicular to each other. But I have not rotated r itself. Let me try to make sure I've drawn it exactly the same. Like that. Okay? All right. Now what I want to know is what are the components of that displacement vector, r arrow, but now with respect to the rotated axes, the new set of axes, x bar and y bar. Okay? So I will now sketch the components of r relative to x bar and y bar. All right, let me use a different color for these components. You see how you would do it? Probably the easiest way to see is start at B and drop a perpendicular to x bar. Okay, now start at A and go out along x bar to that intersection point right there. And that arrow is the new x component of r, but it's the x bar component, right? In fact, I'm just going to call it, I'll label it here, x bar. It's the x bar component of r. And then draw another arrow from there to there, and that's the y bar component of r. So I will label it y bar. And this angle will be helpful between r and x bar, and I'm going to call that theta bar. And I think it's pretty clear from geometry that theta bar is the original theta minus phi. Remember the original theta right up here? There we go. That r arrow makes with x. Now look at the new picture. A little bit busier, but that's what we're working with now. And r arrow still makes the angle theta with x, but the angle theta bar that it makes with x bar is theta minus phi. Okay? All right, but now what is the expression for x bar? That's what I want to write out next. Okay? All right. X bar. Of course, what I mean is this component right here. Still can use trig. You've got a right triangle there with r arrow, x bar and y bar, with an acute angle theta bar and a right angle that's marked. That's a right triangle. We can still do right triangle trig. And the component x bar is hypotenuse, magnitude of r, cosine theta bar. But don't forget that theta bar is theta minus phi. So let's plug that in. R magnitude cosine of theta minus phi. All right, but let's now use a trig identity for the cosine of the difference of two angles. And then that means this can be written as r magnitude cosine theta cosine phi plus r magnitude sine theta sine phi. That's just a trig identity for the cosine of the difference of two angles. But then we remember that r magnitude cosine theta, not theta bar, theta, was the original x component of r. So we just call that x. And r magnitude sine theta was the original y component of r. So we'll just call that y. So now we have the new x component of r, x bar, is the original x component, x, times cosine phi the angle we rotated the axes by. Remember, we didn't rotate r at all. Plus the original y component, y, times the sine of the angle phi. And that turns out to be one of the two important relationships I need. It relates the new x component of the vector in the rotated axes to the original x and y components in the original axis. Now we play the same game for the new y component. So, and, we'll come over here, y bar, okay, now I'm talking about this component right over there of that new right triangle. And again, I just use trig, and I have hypotenuse, r magnitude, sine theta bar, which I can then write as r magnitude sine of theta minus phi. And now I use the trig identity for the sine of the difference of two angles. So I get y bar equals r magnitude sine theta cosine phi minus r magnitude cosine theta sine phi. That's a trig identity. But then we recognize r magnitude sine theta as the original y component of the displacement, and r magnitude cosine theta as the original x component. And so we have an expression for the new y component, the y component of the displacement relative to the rotated axes, y bar. It's equal to the original y component, y, times the cosine of phi, the angle that we've rotated the axes by, minus the original x component, x, times the sine of phi. That's the second important relationship. And those two that I've highlighted, those two angles, or two expressions, relate the components of the vector r relative to the rotated axes in terms of the components of r relative to the original axes and the angle phi of the rotation. All right, now with those two expressions, we're ready now to define a vector quantity. This is how we're going to define it. Okay? I will write it out since it's important, our new formal definition of a vector quantity. And I want it now to be more generic than just thinking about displacement. I picked displacement to start with because I know for sure that's a vector quantity, and I wanted to see how the components of the displacement are affected, changed, transformed when we rotate our axes. That's what I've learned. I'm going to use that knowledge to define a vector quantity in general. Okay? All right, so here we go. Whenever a pair of quantities, I will denote them now because I'm not going to just limit myself to thinking about displacement. I'm going to label them A sub x, capital A sub x, and capital A sub y, to remind you of components of vectors like we talked about in lecture 2. So we have a pair of quantities labeled ax and ay in an xy coordinate system is transformed into new quantities. I'm going to label them ax bar and ay bar by the rotation of axes just described and so we rotate our axes counterclockwise by the angle phi, and we had two quantities ax and ay, and those get changed to ax bar and ay bar. And here's the relationship for ax bar and ay bar in terms of the original quantities ax and ay and the angle phi. Namely, ax bar must equal ax times cosine phi plus ay times sine phi. I'll number that equation 1. And ay bar is equal to, I'll write it like this, negative ax sine phi plus ay cosine phi. I'll number that equation 2. Okay? We had a pair of quantities ax and ay in a coordinate system, xy. We then rotated the axes of that coordinate system by an angle phi, and ax and ay transform into ax bar and ay bar, and ax bar and ay bar are related to ax and ay by equations 1 and 2. Then we define ax and ay as the components of a vector, which we would denote a arrow. Okay? So a vector is defined by how its components are transformed when you rotate the axes of your coordinate system. That is how we define a vector quantity. If you go back up and look at what I did with the displacement up here, x bar and y bar, the two highlighted equations in yellow, the one for x bar and the other for y bar, you will see that those equations exactly follow the pattern of equations 1 and 2 here. Okay? All right, so the upshot of what I just said is we define a vector based on how its components are transformed under rotation of the axes of your coordinate system. That's how we define a vector. Okay? Any quantity is a vector if its components are transformed under rotation, just like a displacement vectors would. Here's something that is going to be an important thing to note. 3. We rotated the axes. We went from x and y, rotated by counterclockwise by an amount phi to x bar, y bar. We did not rotate the displacement vector r itself, and the magnitude of that displacement vector r is clearly unchanged, right? The length of that arrow is completely unaffected if all I do is rotate my axes. But the length of the arrow represents the magnitude of the quantity we're calling a vector. So let's note then. Let's note that the rotation must leave the magnitude of a vector unchanged. How do I write that mathematically? Well, if my vector is the arbitrary vector A, then its components relative to the original axes would be ax and ay, and so the magnitude of A would be ax squared plus ay squared, right? Pythagorean theorem. Now, relative to the rotated axes, x bar and y bar, I would calculate the magnitude by taking ax bar squared plus ay bar squared. But that's when I do that operation, I've got to get the same thing that I got for the magnitude with the original axes. Now you can actually use equations 1 and 2. You can substitute equation 1 in for ax and then square it. And you can substitute equation 2 in, for ax bar I should say, for ay bar and square and add. And do all your math carefully, and you will discover you get this, ax squared plus ay squared. So equations 1 and 2 manifestly obey this, but it has to be true. Let's go back and look at that original picture I had. Now I'm ready to talk about it. See it right here? Let's make sure it's visible here. All right, there are the original axes. Now I apologize for the slight change here. They're called y and z. But there's the vector A relative to the original axes. And then there are the rotated axes, y bar and z bar, rotated by an amount phi, but we have not rotated A, so its magnitude is still the same, right? And we were looking at how the components of A change under that rotation. Okay. Now, let me show you a compact way to rewrite those equations 1 and 2 up above. We'll use matrix notation. Let's rewrite equations 1 and 2 using matrix notation. It's more convenient many times because it's more compact. I will put on the left what's called a column matrix with ax bar and ay bar vertically. This is an example then of a 2 by 1 column matrix. 2 rows, 1 column. That will be equal to. Then we'll have a 2 by 2, a square matrix. And the elements in the first row will be cosine phi and sine phi. And in the second row, negative sine phi and cosine phi. So we have here a 2 by 2 square matrix. And then that gets multiplied by another 2 by 1 column matrix that has the first element as a sub x and the second element a sub y. This is a 2 by 1 column matrix. And this is meant to imply that you use matrix multiplication. Okay? You multiply the 2 by 2 on the right by the 2 by 1 on the right, and you will get the 2 by 1 on the left. The way, of course, you do vector multiplication is to get ax bar, you take cosine phi times ax plus sine phi times ay. So you're multiplying the first row of the 2 by 2 with the 2 by 1 column. To get ay bar, you take negative sine phi times ax plus cosine phi times ay. You're multiplying the second row of the 2 by 2 on the right by the 2 by 1 column matrix. All right, there's even more I want to say about this 2 by 2 matrix, because it's really that 2 by 2 with the various sines and cosines and the angle of the rotation phi. That is what you might call the transformation matrix. It is describing mathematically this transformation of rotating the axes. And so it's that 2 by 2 that's really the important part of what we're talking about. And I want to focus on it a little more and introduce the concept of what's called a direction cosine. There'll be multiple of them, so there'll be plural. And basically what it means is this. What I'm talking about is this. Each element of the 2 by 2 matrix, right? The cosine phi, sine phi, negative sine phi, cosine phi, is the cosine, mind you, of the angle between one rotated axis and one original axis. Okay? Let me show you how that works. And the way we would represent that 2 by 2 matrix in general is we write the elements like this. R, that's the notation, with a subscript x bar x in the first row, and R x bar y in the first row, R y bar x, and R y bar y in the second row. That's just the notation in general for those elements of that 2 by 2, where, for example, the first element, R subscript x bar x equals cosine of angle between the axes x bar and x. That's what goes in the first element there. The cosine of the angle between the x bar axis and the x axis. Let's go back up and look at our picture. There it is. Go up and down here a bit. I want the cosine of the angle between x bar, okay, that's here, and x, right? The cosine of the angle between those two axes. Well, that's just the phi, isn't it? There's no doubt about that. So that would just be cosine phi, which is, of course, what our first element in the 2 by 2 matrix is right up above. Let's do another one, though. How about R subscript x bar y? So that apparently must be interpreted as the cosine of the angle between x bar and y. Yes, that's how we're supposed to think of it. Now let's go back up to the diagram. Now what I want, okay, now let's get rid of some stuff here. I don't want to get rid of too much here. Now what I want is the cosine of the angle between x bar, okay, that's that one, and y, that one. Okay, x bar and y. Now what is the angle between them? Well, I contend that it's 90 degrees minus phi. See that? 90 degrees minus phi. So that's what I need to calculate here. Cosine of 90 degrees minus phi. Now you work out that using, oops, I guess that needs to be a little bit higher. You work that out using trig identity, cosine of 90 degrees minus phi, and you will discover that it is just equal to sine phi. Now that's r x bar y, and that should be the same then as the row in the element of the matrix in the first row, second column, right here. And sure enough, it's sine phi. Then you calculate, I'll let you do these on your own, r y bar x. That's the cosine of the angle between y bar and x. you should find that that's the cosine of 90 degrees plus phi, which is negative sine phi, which agrees with that element right there. And then lastly, calculate r y bar y, which is the cosine of the angle between y bar and y, which is phi, so cosine phi, which is this element right here. Okay. So that's just the kind of generic notation, r with two subscripts. Okay? And each element of the R matrix, or the matrix R, I'll just denote the whole matrix by underlining it like that. Each element of the matrix R is called a direction cosine. It's the direction cosine for the angle between one of the rotated axes and one of the original axes. Now I just want to generalize my picture a little bit to a full 3D view. Okay? All right, so now I want to view the rotation in 3 spatial dimensions. I mean, it's still a rotation where x and y get rotated into x bar and y bar, but now I've got a z-axis, but the rotation is actually about the z-axis, so the z-axis gets unchanged. So we'll have a new z-axis, z bar, that's exactly the same as the original z-axis. So let me draw, gets a little bit more complicated. Let me draw a picture in 3 spatial dimensions, full Euclidean space. Let's see if I can do this. We'll take the common z bar axis to be straight up, so to speak. Then we'll have the original x and original y, where even though we draw it so that it looks, otherwise, the angle, of course, between the x and the y is 90 degrees. Original axis. But now I'm going to rotate counterclockwise about that z-axis by an amount phi. I'll get a new z-axis called z bar, which is exactly the same as the original z. But I'll also get a new x-axis that'll be rotated counterclockwise in the xy plane. So we'll call that x bar, and it will be rotated from x by an amount phi. And I'll get a new y, a rotated y-axis, which we'll call y bar, which will be rotated from y by an amount phi. And in this 3D space, I've got a vector that I'm going to call A. I'll put its tail at the origin, capital A arrow. I'll even drop its projection down into the x bar, y bar plane, and then draw that connection to that with the origin. This will then be a right angle here. And that's basically my picture now, okay? I've got this vector quantity, big A arrow. It's not being rotated, right? It's just sitting there in 3-dimensional space. I've got a coordinate system, x, y, and z. I'm going to rotate about the z-axis counterclockwise by an amount phi. Z bar is the same as z, but x bar and y bar will be different from x and y. And then there's A. Okay? And I want to relate the components of A relative to x bar, y bar, z bar. I want to compare those to the components of A relative to x, y, and z. And for that, I need now slightly larger matrices. The A bar column matrix will be a 3x1 because the A bar now has 3 components. And the A matrix, column matrix, for its components is 3 elements. And the matrix R with the direction cosines is a square matrix that's now a 3x3 because I'm in 3 spatial dimensions, with 3 direction cosines. You take all possible combinations, rx bar y, rx bar x, rx bar y, rx bar z, that's first row, ry bar x, ry bar y, ry bar z, that's the second row, rz bar x, rz bar y, rz bar z, third row. Okay? And I contend that it's pretty easy to write down all 9 of those direction cosines from this picture. Okay? All right, let's do that. Now, the rx bar x, x bar y, and y bar x, and y bar y are exactly the same as what I just did up above. Those are not changed at all. I'm not going to do them again. But the new direction cosines I have to deal with are ones such as rx bar z. Let's think about that one. That's the cosine of the angle between x bar and z. What is that angle? What is the angle between the x bar axis in this drawing and the z axis? Did you say 90 degrees, right? They're perpendicular to each other. But the cosine of 90 degrees is 0. Careful, not 1, 0. So that's one of the 9 direction cosines in my R matrix, and it's a 0. When you're working with matrices, and you have elements of the matrix that are 0, that's good. It makes the matrix easier to deal with. Now, there are other new direction cosines to deal with, but I contend that most of them are going to be 0, like r y bar z. The cosine of the angle between y bar and z. It's still going to be 0. And r z bar x and r z bar y, all 0. And there will be r z bar z. Now what's that direction cosine? Well, it's the cosine of the angle between z bar and z. What's that angle? Well, it's 0 degrees, isn't it? And the cosine of 0 degrees is 1. Okay, so with that in mind, we can now write out the matrix product that we need. I'll write it down here. I have a 3 by 1 column matrix with the 3 components of A relative to the rotated axes. Get this up here a little bit higher. AX bar, AY bar, AZ bar. And that must equal a 3 by 3, make sure I make that big enough, times a 3 by 1 with the 3 original components of A there, like that. So what goes in the 3 by 3? That's the matrix of the direction cosines. The order is R x bar x, R x bar y, R x bar z. That's the first row. Okay, and then R y bar x, R y bar y, R y bar z. And finally, R z bar x, R z bar y, and R z bar z. And then I'm just going to write down right underneath here what that 3 by 3 looks like for this rotation that we're talking about, counterclockwise by an amount phi about the z-axis. The elements are cosine phi, sine phi 0 for the first row, negative sine phi, cosine phi 0 for the second row, and 0, 0, 1 for the third row. Note that this upper left quadrant is exactly what we had in the two-dimensional rotation case. And then the new row we have here is a very simple one, 0, 0, 1, because we rotated about the z-axis. Note that with that row, like that when I do the matrix product to get AZ bar, that rotated component, AZ bar, I'll do that by multiplying the third row by the column here. And with all those zeros in the third row, it's not too hard to show yourself, convince yourself, that AZ bar is exactly the same as AZ. In other words, the Z component of our vector is unchanged if the rotation is about the Z axis, which should seem reasonable. Okay, just a little more I want to say about this whole rotation business, okay, of the axes. Next comment. I want to just generalize this notation, and even though I like the idea of the matrix notation and using a matrix product as a way to relate the rotated components of the vector to the original components, you can even make that notation more compact, because it's still a bit tedious to draw out those big matrices and so forth. Let's use more compact symbolic notation for matrices and a matrix product. Okay? So, and let's not limit ourselves to rotating now about, say, a z-axis. You can imagine any kind of axis pointing out from the origin in any direction in the three-dimensional space, and then you can rotate your axes about that axis. It starts to get hard to try to visualize it, but you don't have to limit yourself to rotations about z. You can have a rotation phi about any axis in this three-dimensional space. Okay? All right, so for any rotation phi about any axis in three dimensions, here's how I'm going to express the relationship connecting the rotated components, or the components of the vector relative to the rotated axes, to the component of the vector relative to the original axes. I'm going to write it like this. It's a pretty standard matrix notation. The ith component, AI bar, is, well, it comes from multiplying a row in the R matrix with the column matrix for the original A components. And that's denoted with a summation notation. I'll use an index different from I. I'll use J, going from 1 to 3. I take an element, the ij element of the matrix R, and I multiply it by the jth element of the column matrix A, where the Rij's are range over 9 different quantities, depending upon what the indexes are, and they're the 9 direction cosines. You just got to get used to the I and J notation, where you use I and J going from 1 to 3, and what it means is that if I equals 1, that means the subscript is, you're to think of it as x bar. If I equals 2, then that subscript really represents y bar, and if I equals 3, that represents z bar. Likewise, if the other index we're using, j, equals 1, it's the second index on the R, notice, that represents x. If j equals 2, that represents y. And if j equals 3, that represents z. Okay? So let me flesh that out a little bit more for you, since you may not be used to this very compact notation. This whole thing on the right represents matrix multiplication. To get the ith row of the rotated matrix A bar, you take the ith row of R, and then you work your way across the columns J, multiplying each column by the corresponding AJ. So you work your way across row I, and you multiply by the elements in column J. So, for example, if we let I, okay, if we choose, for example, the index I to be 1, then on the left we have A1 bar, and that's given by the sum over j going from 1 to 3. And remember, the I has been chosen at 1, but the j is summed over ranging from 1 to 3. So this will have terms like R11 times A1 plus R12 times A2 plus R13 times A3, which is exactly what you would get if you multiplied the first row of the R matrix with the column matrix A and added up as you worked your way across. Okay? Now, using the old notation, this would be AX bar equals RX bar X times AX plus RX bar Y times AY plus RX bar Z times AZ. So the upper line is just a new way to represent the lower line. Okay? All right, so now we have a very compact way to represent this rotation of axes and to relate the components of the vector relative to the rotated axes to the components of the vector relative to the original axes. And it's this matrix of direction cosines that make a vector by definition. And there's just one more thing I want to talk about, and it refers back to a point I mentioned earlier. So this I'm up to 4. And that is, if I rotate my axes about any axis in three-dimensional space, I'm not rotating the vector. The magnitude of the vector is unchanged. That has to be true. The magnitude of the vector, when expressed in terms of its components relative to the original axes, has to be the same as the magnitude of the vector when expressed with its components relative to the rotated axes. That requirement puts a constraint on these direction cosines, the R, I, J's. And I want to talk about that now. Restriction on the 9 RIJs, the matrix of direction cosines. It's all based on the fact that we require the magnitude of the vector, or the magnitude squared, to be unchanged. So if I use the rotated axes, it's A bar magnitude squared must equal the original, the vector relative to the original axis magnitude squared. Remember, magnitude squared of a vector, another way to write that is the dot product of the vector with itself. So that could also be written on the left as A bar vector dot A bar vector must equal, and on the right, A vector dot A vector. But when we take the dot product of a vector with itself, we just take each component square and add them. Basically, the Pythagorean theorem. So on the left, I'll have a sum. I'll use the index, I'll call it I, from 1 to 3, of AI bar squared. And I got to do the same operation on the right for the A, but I have to use a different, well, I don't have to use a different index here, but these are just two separate sums, but I'll still use I from 1 to 3 of AI squared. That has to be true. Now what I want to do is I want to use the relationship between the, if you like, the rotated components, AI bar, and the original components. And that one is the expression I just wrote down a few moments ago. AI bar equals the sum j going from 1 to 3 of Rij times Aj. And I'm going to substitute that expression, that whole thing, mind you, like that, up in there, and square it. Okay, looks a little bit complicated, but got to have some physics courage. So when we do that, we will have, well, on the left, we'll have this sum, I going from 1 to 3, and then we'll have this expression right here, put a little asterisk by it, sum over j, rij, aj, but I got to do it twice, right? It's squared. So I'm going to have, I'll use some parentheses for grouping, sum j going from 1 to 3, rij, aj, but I got to multiply it by itself, right? Because it's squared. So it's another sum like this. But I can't use the j sum again, because that's already been used on this left side. So I just have to use a different dummy sum index. Any letter that's not an I or a J is fine. I'll use K from 1 to 3, and then it will be R, I, K, A, K. Note in the second parentheses, K plays the same role as J in the first parentheses. And that whole thing on the left must equal sum I going from 1 to 3 of AI squared. Now, I still have to get the two sides to be equal. So that messy stuff on the left ultimately has to boil down to one sum going from 1 to 3 of the components squared of A. So somehow, the other two sums and the combination of the r's have to be gotten rid of on the left side. Okay? And so, here's what has to happen. To get the equality of the two sides, I contend that we must have the following result. The sum over the I index, going from 1 to 3, of the product of the r's that we have here. Look carefully. That's rij, rik. I took just the product of the r's and one of the sums, the I sum, because it's the I index on the r's that's common in the two terms, right? rij, rik. And I contend that that sum over I must be this wonderful quantity that some of you may have heard of before, seen before, called the Kronecker delta jk. That's what it's called. The Kronecker delta, with the Kronecker delta always has two subscripts. They could be any letters you want. Here they're J and K. And really the Kronecker delta has very simple, wonderful properties. Namely, delta jk equals 1 if the indexes j and k are equal. And delta jk equals 0 if the indexes j and k are not equal. Very simple property. Okay? But I contend with that property, I'm going to be able to get the two sides of this expression to actually indeed be the same. Okay? All right, now, with that, the left-hand side, I'm going to replace the sum over I and rij, rik with one Kronecker delta, delta jk. So then the left-hand side has now simplified to this. Notice everything that's being multiplied is all just scalars. I'll have two sums. I'm going to bring them out front. A sum j going from 1 to 3 and a sum k going from 1 to 3. I have the Kronecker delta jk, aj multiplied ak. That's what's left on the left. And on the right, I have the sum I going from 1 to 3 of ai squared. Now, Kronecker deltas in sums, like we have on the left, are wonderful things. Because, well, first of all, the Kronecker delta jk is 0 for all combinations of j and k that aren't equal to each other. So when you have a Kronecker delta in a double sum like this, it will always exhaust, get rid of one of the sums. Doesn't matter which one you want to get rid of, because these dummy indexes just stand in for summing from 1 to 3. So I'm going to get rid of the k sum. Okay, and it changes every symbol that was a k, that was a k into a j. So what I'm left with on the left, because of the Kronecker delta, is one sum. It'll be over j, going from 1 to 3. The Kronecker delta has been exhausted in eating up the k sum, and I just have aj squared. And I have shown now that the two sides are indeed equivalent, right? Doesn't matter that the label on the sums is different, I and j. Doesn't matter at all, because all that stands for is the procedure, the recipe for taking the components of the vector in the original coordinate system, squaring them and adding them, the three of them. The two sides are clearly the same, okay? So the key thing then that has to be true is right here. That's the property that this R matrix has to have. When you sum over one of your indexes, I going from 1 to 3, Rij times Rik, you must get the Kronecker delta Jk. That's the pattern, that's the property that the R matrix has to satisfy in order to keep the magnitude of the original vector unchanged. What does that mean exactly? Because it seems pretty abstract. Well, let me just show you one other way to write that. And that'll be just about as simple as I can get it. I'll write it down here then. So we require that sum I going from 1 to 3 of Rij, Rik equals the Kronecker delta Jk. Now, let me remind you about something called the transpose of a matrix. All you do to get the transpose of a given matrix is swap the rows and columns. Column 1 becomes row 1. Column 2 becomes row 2. And column 3 becomes row 3. Do that right. And so when you use this double subscript notation for a square matrix, like the Rij and the Rik, it's easy to talk about the transpose. Just reverse the order of the two subscripts. So another way to write this requirement, I going from 1 to 3, is instead of writing Rij, write it as R transpose Ji. Just reverse the order of the indices. Notice I haven't done anything to the second R matrix. So that symbol T up there stands for the transpose of the matrix R. But now, if you look carefully, you'll notice this is a sum, I going from 1 to 3, of Rji transpose Rik. Notice that these two inner indexes are now the same. And this first index j is the same as the first index on the right, and the last index k is the same as the last index on the right. That's the prescription for matrix multiplication. And therefore, what I have on the left says, take the matrix R transpose and multiply it by the matrix R. And when you're done, you'll have a 3 by 3 square matrix on the right. But it will be a special 3 by 3 square matrix with its 9 elements, where the elements along the diagonal are all 1, because those are the places where j and k are equal, and all the elements off the diagonal are 0. Well, that's a very special matrix called the identity matrix. And this would be then a 3 by 3 identity matrix on the right. So that turns out to be the mathematical property, at least that's the most succinct way to describe it, the mathematical property that the matrix of direction cosines must have to preserve the magnitude of a vector under rotation. You multiply the rotation matrix by its transpose, and you must get the identity. That will come up from time to time as we're dealing with vectors. Okay? All right, so that's all for this for this video. And we'll be now picking up in class in chapter 1, where I'm leaving off here. And that's all for this video.